Luckily, we have today David McAllester, who doesn't need any introduction, so instead I'll introduce the Research at TTIC series.
Thanks, Maddie. I've been using this slide for 7 years. So 7 years ago, we had Alpha Zero that learned to play chess, Go, and shogi just from the rules of the game and self-play. So when this came out, I and many people sort of wondered, well, can you do that for math? Math is a kind of formal game. You build a system that learns to do abstract mathematics just by self-play. So just recently, this summer, there was this sort of probably dramatic development, alpha proof. So I'm going to spend the first half of this talk talking about something that's not my research at all. I'm just going to survey what's happening in this mathematics language model universe. So alpha proof made a splash at the IMO. So this is the International Mathematics Olympiad. It's held every summer for high school students. And many people at TTI have actually participated in this, or at least some. The Olympiad consists of 6 problems, and it's 2 days. You get 1 day to solve the first 3, and the second day you solve the second 3. Deep Minds, Alpha Geometry solved a geometry problem, one of the IMO geometry problems, and then this Alpha Proof, which is a different program, solved 3 of the remaining 5. So, and those solutions, you take the solutions, you give them to the judges, they were judged, and they got a silver medal in the IMO. However, it took them, that computation to solve those problems took 3 days. The high school students get 1.5 hour per problem. So this is presumably an enormous amount of computation. And we don't have a paper. There's a blog post, and I'll be talking about the blog post, what we know from the blog post. Okay, so this talk, I want to make a distinction between 3 cultures. So there's...
I'm curious for the IMO. Do you know how... I've never actually done the IMO, I'm not clear about it. So how, like, if you take one of the, if the participant and a below median participant, would they be able to solve most problems if given
enough time?
Not 2 weeks?
Does somebody else know the answer to that question?
No, I think the median participant can only solve 2 problems.
No, in the exam, but if they have
the problems are such as if you can solve it now, you can probably solve it at the exam. If you cannot solve it now, you're never going to solve it, probably unless you somehow improve.
So for high school students, time is not an issue.
Yeah, you either are good enough to solve it or you're not good enough to solve it. No, it doesn't help. But there's some sort of stress, right?
Very concise answer. Okay, so there are these 3 cultures. So there's mathematicians, and I want to think of mathematicians as users, right? They're going to be the people who are going to try to use this system to help them in their research. And most PhDs in mathematics today, the person getting a PhD in mathematics was not trained in logic. 30 or 40 years ago, people would be trained in ZFC, the foundations of mathematics, and they would know the logic and all the, they would look at the independence of the continuum hypothesis. But these days, the logicians and the mathematicians can't really talk to each other. And then there are the deep learning researchers that are all about transformers and all kinds of issues that arise in deep learning. And all of those issues are, again, sort of oil and water with the mathematicians. And then there are the logicians. And this is probably the smallest group these days because logic is in the doghouse. Right? The logic was the keystone of AI 40 years ago. But I'm going to talk a lot about the lean system. So it turns out that alpha proof at the bottom uses lean. And lean is a formal verifier written by a logician community that can actually sort of certify correctness by reducing it to the formal logical axioms. And lean is the sort of any system, any modern system, any current system that is really completely verifying is somehow resting on this one system, lean. That's not completely true, but it really dominates that niche. So I'm going to go through these 3 communities just to show that what's happening. So what's happening among mathematicians? So Terry Tao, Fields medalist, very recently, September 23, a year ago, organized a group effort that machine verified one of his own new papers. So this was a group effort. They did this thing called a blueprint, where they take the theorem they're trying to prove and they say, well, this is going to follow from that and that and that. And they build this big tree of the structure of the proof, and then they delegate pieces. Right? So there's somebody that works on this one connection in that blueprint. So it's a group effort, and they get it done. He gave a talk at the IMO on this project, and he said, you can know how good of, you can know how competent someone is at this, or know whether or not they've solved the problem without having to check it yourself, right? Because they come back and say the machine checked this step, and you can just believe them. And if somebody's good at this, you don't have to. It really reduces the burden in the communication because you don't have to check each other. Okay. Peter Schultz, also a Fields medalist, this was a little bit longer ago, 2 years ago, organized a group effort to machine verify what he considered his most important theorem. I don't understand condensed mathematics or perfectoid spaces. But you don't have, the people who develop Lean don't have to. The user pushes this theorem through. And again, it was this group effort. Tim Gowers, who's also a Fields medalist, is now focusing as one of his main enterprises on improving the level of automation in these machine verification systems. Kevin Buzzard, who's works in number theory and relating number theory to group, representation theory, which is how the Fermat's last theorem is proved. Not that I know much about that. But he's announced a project to try to machine verify Fermat's last theorem. And apparently this is a monumental task. Okay, research. Okay, so I'm going to call these.
So just for the Terry Tao and Peter Schultz methods, how much of these relied on automatic proof or automatic translation from English to Lean, or how much of them is just?
So when they build this blueprint, my understanding is each node in this blueprint has a formal machine-readable state.
That was handwritten,
That
or
was
there was
handwritten.
Okay. And then the steps between them were auto-proofed with
No, somebody sat down with Lean.
So it was completely manual with Lean.
Well,
Everything was
Lean
manual.
provides some level of automation. So you say, Lean, do you see this step? It says, no. You break it down. It's Lean, do you see these steps?
Okay, but the automation is the level of proving, not the level of translating a proof from English to like
Right.
Lean.
If a step like that requires intermediate lemmas, you're going to have to write those intermediate lemmas in a machine-readable form. Okay, I'm going to call these things language model program generators, proof generators. Sorry, language model proof generators. And there was a paper that was I think, if not the first, a very early paper in this space. I just want to point out that this space is non-trivial. The space of language model proof generators has a significant, 30 or 40 papers, significant literature. So this paper has 200 citations. Language modeling for automatic theorem proving. The state of the art among published papers is something that just appeared in August called DeepSeek 1.5. And that's a Chinese company. And I'm going to talk a little bit, that's a nice published paper, so we know what is under the hood there. So I'm going to talk a little bit about that. Logicians. So there's three communities, right? The mathematicians, the deep learners, and the logicians. So I talked about this Lean system. Okay, so where do I fit into this? So I have built this system I'm calling Alfred. Alfred is named, there's a programming language called Haskell. And Haskell is named for Haskell Curry, who's a logician. So I'm naming my system Alfred after Alfred Tarski. And there's some deep philosophical digs in that choice. If you have time, we'll get to. Basically, I'm allergic to constructive mathematics. Lean is fundamentally a constructive mathematical system, and it drives me crazy. So I'm trying to build an alternative to some extent, just to show you don't need constructivity. Okay, how do we want to think about this problem? What is this problem of language model proof generation? So I'm going to talk about, this is the architecture really of Lean. So in Lean, you have something you're trying to prove, and Lean has a set of things called tactics. So a tactic will take the thing you're trying to prove, written in a formal notation, and try to prove it. But typically it can't prove it, but it will give you back a set of proof obligations. If, okay, you're trying to prove A, well, you could prove A if I could prove B, C, and D. And then you decide either you want to take a different step or you prove B, C, and D. So a tactic is something that takes a goal, I'm going to call these statements a goal, and it produces a set of sub-goals. If it produces empty sub-goals, it proved it. So we've got this thing that can take a goal and produce a set of sub-goals. And just to give when I gave this talk, I gave a similar talk at our 20th anniversary workshop, and people were asking me, what is a tactic? So I thought I'd give some examples. For example, if you've got a goal, especially a goal that the machine has generated, and it's got some expression that you want to simplify, you can call a simplifier tactic. Or you could say, I want to prove this by induction on a specific well-founded order. Or you could say, I want to use this lemma, that lemma, that lemma. This is going to follow, name the lemmas. And that helps the tactic a lot. Okay, so if you think about this is going to generate an and/or, will in principle generate an and/or search tree, right? I take something I'm trying to prove. I'm going to apply a tactic. I get a bunch of things that if I prove all of them, I can prove my goal. So that's like generating an and branch. I want to get an and over those. But I also have the choice of tactic. And the choice of tactic is like an or branch, right? I'm free to choose the tactic. One tactic is going to be better than another. So in principle, you've got this and/or search tree. So there was this paper from a couple years ago called hypertree proof search. And I'm old. So I remember when AO star search was a big, significant algorithm for and/or search trees. So then the question is, and so this hypertree proof search was basically, taking this old algorithm, AO star, and applying it to this and/or search tree. Okay, it turns out this literature has various architectures. So what I just described is an and/or search tree. And I can apply, classical AI algorithms, these generalizations of A-star search to and/or trees. Or you can do an or search. So I said a tactic takes, you can think of a tactic as taking a set of goals and replacing one or several with a different set of goals, or more goals, or maybe fewer goals. Maybe it solves some. So if you think of the nodes in your search space as a conjunction of open obligations, then it becomes an or. You just keep track of the whole and. Am I making sense? So you can just do an or search. And a lot of the current systems, I believe, DeepSeek 1.5 is just using an or search. Or this thing was kind of shocking to me. One of the leading systems does whole proof generation. So you say to Lean, or you say to your language model, don't just suggest a tactic. Prove the whole thing, start to finish, a sequence of tactics. So that's whole proof generation. And then you do that non-deterministically. So it tries and tries to solve the whole problem. And that's fewer calls to the language model. So you can do, so it's reducing the computational cost, so you can do more search maybe. And they had success with that. So you can do whole proof generation. Question?
So I had two questions. So first of all, how is either the and or search tree constructed? Like, do we give it an instantiation and then it finds new branches and tactics? And secondly, how does it find a new or branch? Finding a new or branch is almost like, it's like requires creativity. Or, I don't know. I mean, how does it magically find a new or branch without any information?
Well, it's a language model.
Okay.
So how does it pick the next word? That would seem to require creativity also. So it's picking a
The
tactic.
classical methods, how would they? You would need to give them a set of tactics, and they'll.
Well, the old classical algorithms were solving things like Rubik's Cube, or maybe not Rubik's Cube, but we're solving things that had well-defined move spaces. When you play chess, right, you're one of the players, and it's a min-max search.
Right.
So the sign of the nodes is flipping. It's very much like an and/or tree. If the nodes are classified as win or loss, it would be an and/or tree.
So there, the task, the complication is not finding the tree, but like going through the right path to provably either get
Right.
to the final statement or win the game, depending on chess versus math.
So it's very much like a chess algorithm.
I see. But for like proving a theorem, I would assume the tree is not known a priori, unlike a game.
Well, it has that infinite OR branch, which is what you were pointing at. So what you can do is you just build the tree by seeing what the language model proposes, and then take the proposals from the language model and defining the tree.
Okay. So output generation and repair. What is the repair aspect here?
Well, I was sort of ignoring that. So I guess
I noticed.
So I didn't read it in detail, but presumably when you generate a whole proof, you try to I don't know. You could do something like BERT to change some choices in the sequence. I'm not sure how the repair works. There was a repair mechanism.
Do you know what data set they're using to train?
I don't. I'd have to go back and look at the paper.
When you
I'll
said
say more about what alpha proof is using.
when you said non-deterministically, does that mean they sample a lot of generations from the models using some sampling?
That's my understanding.
And then take
Right.
some.
And you can also change the prompt,
Right,
right?
yeah.
So you can change the prompt in a way that avoids repetition. It changes the answer. I've heard some people say you always want to be running at temperature 0 because that's giving you the best response, but varying the prompt to get variation.
I see.
Okay, so now what I'm going to do, I'm just saying that what are the choices, what are the design decisions? So one of them is and or whole proof. Another choice is do we put natural language thoughts in the nodes, right? So when the language model proposes a tactic, it might say, why it thinks this is going to work in English. Okay. And then you can put that in the in your formal theorem proving proof tree is going to have English annotations at every node. And that seems to be important. So another question is the reward function. So in DeepSeek 1.5, they make a big deal out of intrinsic reward. This is something that comes out of the reinforcement learning community. So intrinsic reward means you play. You don't have a reward. Your reward is your success in playing. And it's a diversity thing. And what they do here is they, especially when you're starting this thing, actually proving a theorem is so hard that your reward signal is too sparse to train it. Right? So if you never prove anything, you never get any reward and you can't train. So what they do is they set up an intrinsic reward where they're simply trying to enumerate new states that they can reach. So they reward the system for how many distinct states it can reach in its search. And by increasing the number of distinct states, they somehow increase the probability that they're going to find a solution. And so it's really a simple idea. So DeepSeek, among the published systems, this seems to be the state of the art. It uses whole proof generation, which is a little bit surprising, but there's an analogy with games here where you think of whole proof generation as a rollout. Right? So in Go, it was a big innovation 10 or 15 years ago to replace the static board evaluator by rolling out the game. Each player plays and you see who wins when you roll out the game to the end. So they're using whole proof generation as a kind of rollout. And now what typically happens in this is the language model suggests a complete rollout, whole proof generation. And then you start feeding it to Lean. And at some point, Lean can't parse it, or Lean can't verify, what the machine expected to happen is not what Lean does. And so it breaks. Whole proof generation breaks. And they take the place where it breaks and they cut it off, but they take that whole proof generation, each state in that whole proof generation, they take as a new node in the search tree that they can expand from. And then they grow a search tree that way. And it's an OR search tree. And they use Monte Carlo tree search, similar to Alpha Zero. Monte Carlo tree search. So in the old days, I'm not familiar with this. In the old days, you would have a chess program, right? And the chess program would use iterative deepening, right? It would completely do an alpha beta search to a certain depth, and then do a min-max backup of static board values. And then it would go one ply deeper and use information from the previous depth to help select moves. In Monte Carlo tree search, you grow a tree one leaf at a time by starting at the root and descending into the tree, trying to follow good moves until you reach a leaf and then grow that leaf. And then you go back to the root and do it again. And that's how Alpha Zero works. And they do that. They use Monte Carlo tree search. And they also put English thoughts in every node.
Used as part of what are they used for? The English thoughts.
They when you generate from that node, you feed the English thought back to the language model.
I was just curious, so is there a way to think about, so Monte Carlo tree search is in some sense, okay, you're not looking at everything in a subtree, but you're looking at enough things so that you have enough information to make future decisions maybe, but you're doing this multiple times. Previous thing was you create a subtree, maybe create a smaller one, and then so maybe you get more forecastability if you do like Monte Carlo or tree search, you can go like deeper. But is there some notion of understanding, okay, if your task is, okay, is there are multiple ways to win at the game, let's say like chess, versus let's say there are only few ways to perhaps prove a theorem. Is there a trade-off here? Like you would want to maybe do or not do Monte Carlo tree search based on how much signal there is?
So Monte Carlo tree search is, in some sense, I mean, there's a lot to say about it. In some sense, it's more interesting than this iterative deepening. We developed this algorithm for armed bandits, the upper confidence bound algorithm. Right. So you're keeping upper confidence bound statistics at each node of the tree to estimate an interval over which you think that value is. I don't know if that's answering your question.
Yeah, like my question is there a depth versus breadth trade-off here, which depends on the task? Like if you have like...
Well, let's assume we're doing the Monte Carlo tree search. Right. So you've got, so basically what they're doing is so you've got an OR branch. Think of them as a bunch of arms in a bandit problem. Right. And they apply a UCB algorithm. Right. And that's supposed to be addressing this depth versus breadth issue.
Right.
It surprises me a bit that the reward for the reward is to generate many new nodes, because I think one of my fears is like in the rules of logic there are many, like for example one rule of logic is to prove A, you can instead prove A and B for any arbitrary B. So there are a lot of ways to like manipulate a target that makes it, that's either worthless or makes it harder even. And at the end of the day, I don't know, when I do maths, normally the goal isn't to generate a billion nodes, it's to find the one short path that actually leads to a solution. So this surprises me. Are my fears unfounded or?
I have no answer to that. I don't know. It worked for this, I mean, it improved their performance in this case. And one thing to think about is the machine, the person, can do this very quickly. Right? And it can do it in parallel. So it has a lot more time. So you could think, if you could do a whole analysis in milliseconds, maybe that would change your,
Did you know if this thing about treeing out a lot of nodes, was that the only reward function, or was that just one
believe that over most of their training, that was the only reward function. I mean, at some point they may have, once they get a less sparse reward, they can switch.
But so is there any, I mean, why does the model even incorporate what the goal theorem even is?
Well, you're enumerating statements that imply the goal. That's one way.
Oh, you're going backwards.
Going backward.
Okay.
So how many different things imply this goal?
It seems like if you actually get back to the axioms, then that
Yeah.
means that you've, but that's almost, if you just want to treat a lot of things, you actually want to go away from the axioms, probably. You want to
Well,
go
all
to
the intermediate, so you got this big tree. The depth in the trees is sort of corresponds to how far you are from the goal, how far you are between the goal and the axioms. So you are spanning that space.
Your set of applications is null once you reach the axioms, if I understand your language correctly.
Say that again?
Your set of applications is
It becomes
empty
zero.
when you have
Right. Exactly.
I mean, this maybe doesn't sound too ridiculous in terms of how we do math. I mean, you start an expression, you try to start simplifying it. So what does simplifying mean? You take it and then you try to rewrite it in a bunch of different ways, hoping that one of them maybe, would look familiar with something, right? But
But if your only goal is to write it in a lot of ways, you can write it in really
more complicated ways.
a lot of
More
pointless
complicated ways. That's true, right? I mean, it's true, right? We try to write it in a bunch of simpler ways,
Right.
Yeah, but we try now. Let's factor out something. Let's open it up. Let's take a common denominator for this expression, right? I mean,
Right,
some
but
of these.
treating lots of stuff makes perfect sense. I'm just curious
Yeah,
how.
I'm also. I mean,
Yeah.
this also seems a bit crazy.
Getting insight into deep models, into deep model phenomenon is really fun. Okay, this is a image from the blog post on alpha proof. So let me try to explain so our knowledge of alpha proof is basically this image, this figure. So we start with 100 over here. We start with 100 million informal English stated conjectures or theorems. Now, how they got 100 million, I don't know. They probably read a lot of math journals. Sorry, a million. Sorry. Read a lot of math journals, and they get 1 million English or whatever, natural language statements. Then they have a formalizer network. So the formalizer network takes the English into a machine-readable form. And it could get it wrong. In fact, it's intentionally non-deterministic. So for each of their English natural language theorem statements, they're going to get 100 different formalizations on average. Okay, so that's this second box. So now we have 100 million formal statements. Now the formalization could be wrong, so the statement you get could be false, right? Reasonably likely that something like half these statements are actually not true. So what they do now is they have a solver network. It takes one of these statements and tries to determine its truth value, absolutely, using lean. And it's going to use some kind of curriculum learning. So maybe some of these are really easy to falsify. You got the translation wrong, it's obviously false. So then they start taking the ones that they can prove, whatever they are, and they start building a corpus of formal proofs. It's like a replay buffer, sort of almost. So they got this corpus of formal proofs. They don't say how big that is, but it's some subset of this.
But these are proofs that have been verified.
These are right. So the solver is going to solve some fraction of the 100 million. For each one it solves, you've got a formal proof that you throw into this database, and then you can use that database of formal proofs to train your network to be better at selecting the tactic that worked. Right? And then it's a feedback loop. So as you're training this prover, this is the solver network. As you're training this prover, as it's getting better, you're getting more formal proofs. So it's similar to a self-play. It's almost a self-play bootstrapping phenomenon.
So how is the formalizer network trained?
That I don't know. We have this figure.
I mean, you probably don't know, but I'm actually curious. And this formalizer seems so. I'm curious, but in the informal problems, are they things that like in one or two sentences contain all the formalism, or like because if I think of like a typical paper or something like that, a formal statement would be if you take it out of context. If it would not like I have to read the entire paper in order to be able to formalize.
To even parse the statement of the theorem.
Yeah, exactly.
Right? I don't know how that's addressed. It might be that they just take the English word, rumble space, and stick it in there.
But then you can prove it, right? I mean,
And you can't prove it, right? No. So I think that somehow they're interpreting all the.
I mean, I think there's two options. Either they only take statements that can actually be some statements in some fields. Maybe the statements are such that can be formalized, or they're actually feeding the entire text in a highlight into the formalized.
So I don't know how it works. I mean, one idea would be you sort of stratify the math by some kind of dependency graph. And so, when you formalize something, you've got formalizations of terms that it's using.
These 1 million informal problems are actually data in the wild. It's not something that they generate.
My assumption is it's data in the wild.
So the how is the formal proof set initialized? Because that seems crucial.
It's empty.
It's empty. I see. So the training set, I'm confused. Like how is the training even happening? Like I can, as a model can just start learning junk formal proofs and keep adding them back
Well,
to
by formal proofs, we mean we're taking a statement and proving that it's true or false. So that's a really strong constraint on the formal proof. Settling the statement.
I agree. But let's say it's something like lemma 1, true. And that's a formal proof, let's say. Then it could be that
proof
lemma
would
1 is
typically involve
false.
a bunch of calls to mean tactics.
Oh, I see. So like a
You get
formal
you
method
get a
is
proof
actually
tree. You're storing the whole proof tree over in a set of formal proofs.
maybe I'm confused. What is the solver? So there's a solver network and then there is the formal verification tool like Lean.
Right.
And initially you have 0 formal proofs. So the set is empty. And
You have some statement.
problem. Yeah, you have some formal problem. Like let's say I don't know, a square plus b square is a square b square 2ab, something like that maybe. And the solver network takes that statement and outputs true.
No.
It doesn't output true.
It outputs true together with its proof.
True together with its proof, and then the formal. Oh, I see. So then once it is in the formal proof, it's known
You've
it's
got,
correct.
you've got the whole proof.
Okay,
I mean, that's what you're training on.
I see.
It's the proof.
So you're generating the proof.
This is probably. Do we know that all formal problems are either true or false? Like, is that
That's a deep question.
Okay. I've heard tell of these dragons called paradoxes. I don't want to.
Well, there's the continuum hypothesis, which is known to be independent of the axioms of ZRC. So is it true or false? These big philosophical.
I mean, the main question is just if you start giving it problems that, like what do, right? The core question is just, do we know that every single formal problem that
We know that if we get a proof, it's true.
Okay.
wait. Why is whether the undecidable problem is true relevant here? What you're trying to do is not to decide whether something's true or false. You're just trying to find if there's a proof or there's a proof of a counter statement.
Okay.
But it's a fascinating question anyway.
But that's
Are
like-
mathematical statements true or
Well,
false?
fine, but it seems irrelevant here, right? Because we know that there are
Yeah, I
definitely
agree.
things that don't have neither.
I agree. Right. It's irrelevant.
What is the solver network? Is it initialized with some pre-trained language model, or like
that I don't know.
when the training starts? Is
Presumably there's a
this?
foundation model.
But is it like a pre-trained foundation model or like something trained from scratch?
I would presume there's a foundation model that's been trained with code.
I see.
And then
Okay, so in the blog post from OpenAI, there's a last paragraph. It's very unsettling. And this last paragraph says they're also experimenting with proofs generated entirely by natural language, no lean. And they say that we also tested this approach on this year's IMO, and the results showed great promise. I have no idea what that means, but it's scary. And I want to make an analogy here with.
Where is it scary?
Well, let me do one more slide. 01 just came out, right? And Terry Tao has a post on Mastodon where he evaluates 01 as as an assistant to a research mathematician. And he got into trouble. He got a lot of complaints about this statement. I'm not completely incompetent graduate student. But what's weird here is that there's no formal verifier at all, under my understanding, underlying 01. It's pure language, right? So this is saying that pure language, I mean, it's opening the possibility that you could build something that was, a brilliant grad student helper. It never touched formal proofs. Right?
What do you mean never touched formal proofs? I mean, but during training, you don't know if they touch formal proofs.
Well, presumably 01, I don't know how they trained 01, but
I would be stunned if they didn't train on the formal proofs, because that doesn't make any sense.
well, we don't know.
Why?
They're trying to have a completely general purpose.
Train it on code. If you train it on code, why wouldn't you train it on?
Well, the question is, was Lean involved in the training of 01? That's the question I would ask. Did they have a formal verifier involved in the training of 01? My guess is no.
But if you mean involved in online, but if they actually fed it as training data lean proofs, because that I'm sure they did. I don't have the inside information, but again, I mean.
Yeah, I would agree with. I expect that's true. That they fed it lean proofs. But I don't think it's. But then the question is, when it thinks it's doing this long chain of thought, right? Are lean tactics appearing in their chain of thought? I would guess no.
I guess one question would be, presumably, I don't know what Terrace was doing in his experiments, but I don't know if he was getting it to write lean or if he was just getting it to write natural language proofs.
You're just talking to
But right, and I'm sure it's trained on lots of natural language proofs, and it might not be clear whether even training it on lean code makes it better at writing natural language proofs.
That's the question. My intuition is that it's just natural language to natural language.
But is there a problem with that? I mean, if all
Yeah, I mean, there is no lean involved in training of a graduate student.
Right. Okay, what have I been trying to do? What's my Alfred? Am I unnerved by this? I am unnerved by this. The idea that I wanted to tell one more story before I do this. Someone told me that they were trying to prove a concentration inequality, high confidence concentration inequality, and they talked to 01. And 01, after some prompting, actually produced a good one. Not only did it produce a good one, it produced an argument. And if it produces a good argument, you don't need it to be perfectly correct. You just need to see that it's true, right? You need to be able to debug it, right, and see that it's true. So he got the answer and he got the proof that it was true from 01. Okay. Here's a fundamental. I think this is a really interesting fundamental question about the future of computer science. What's the role of algorithms? Right? Our language model, our algorithms. Presumably compilers are immortal. We will always use compilers. Compilers are super efficient at translating, quote, high-level expressions into machine code. And there's Lean has all kinds of algorithms in it. It's got decision procedures for linear arithmetic. Alpha geometry is a real cheat, in my opinion, in the sense that it relies on this Wu's algorithm from the 70s, which is an algorithm that can basically solve sort of basically a decision procedure for a certain fraction of geometric problems. So the question is, what's the role of algorithms going forward? And what I'm really interested in is can lean be strengthened? So I've been trying to build a competitor for lean, and I'm calling him Alfred. And I'm trying to take a classical algorithmic approach. Can we have better algorithms for logical inference? And there is a significant literature on these SMT, sat modulo theory. So sat solvers from 40 years ago are able to solve very large Boolean satisfiability problems, and they can be integrated into additional methods that are sort of semi-algorithmic in the sense that they're algorithms, but they're sort of heuristic at the same time. SAT solving involves all kinds of heuristics about which variable to branch on. It's very, I would call it an algorithm. So I'm building this system. So now I'm on slide 20 out of 57.
Yeah, we're a minute 45 out of that. Or 40 out of 55.
So I'll end soon. I'm not going to do all these slides. Most of the slides are about logic and the foundations of mathematics, which is another talk. But I want to give a demo. So at the 40th anniversary workshop here, I made a public statement that I was going to have something people could use by now. So that was almost a year ago. And I'm not ready to give anybody anything, but I do have a demo. So the Schroeder-Bernstein theorem. So the Schroeder-Bernstein theorem it says if I take two sets and I have an injection of one into the other, an injection is something that does not map two elements to the same element. Right? So, and an injection in the other direction, then there exists a bijection. So if these were finite sets, the first thing is saying that if I go from A into B, then A is a smaller set than B. And if I go from B into A, then the reverse is true, so they must be the same size, so there's a bijection. That's for finite sets. But this theorem holds for arbitrary sets. So I discovered this new graphic technique, which is taking a picture of my dirty whiteboard. So this is two sets. I'm calling them S and W. And I've got an injection of S into W, which simply, think of these as the natural numbers. It simply adds one. And the function going the other way is adding one. So I've got two injections in both directions. So that means so the claim is, for Schroeder-Bernstein theorem,
But he's not using one of the nodes, so it can't be. The domain is
the claim is that there exists a bijection. So let's look at this node, this point right here. This point right here is not covered by W. So if I'm going to build a bijection out of these arrows, this one has to be covered by F.
This is, I think, a clarification question here.
This is infinite, it goes down infinitely.
Okay. That makes sense.
Okay, so this thing has to be covered by F, right? So I'm going to have to use this pair. I'm going to build the bijection by selecting pairs from these two functions. This pair has to come from F. The map has to use F here. Okay, so if it has to use F here, it means this one is not available to be used by W, right? Because if I use W, then it's not a bijection. I've got two things going to the same thing. So this one can't be used by W. If this can't be used by W, this one has to be used by F. So I said if this one has to be used by F, so does that one. So it propagates. I'm saying, well, what do I know has to be used by the S to W map? And if it propagates, it says if this one has to be used, that one has to be used. It turns out if that one has to be used, then that one has to be used. And here's your bijection. You're picking pairs from for every point you're picking pairs from F or G, and you're stitching together those pairs. And the question is, can this always be done for infinite sets? So here's the Alfred formalization of the theorem. Actually, it's an Alfred formalization of the proof of the theorem. So this is the Schroeder-Bernstein theorem. I say let S be a set, let W be a set. Suppose there exists, inhabited is going to mean exists. Suppose there exists an injection from S to W. Suppose there exists an injection from W to S. show, this is what you're going to try to show, that there's a bijection. And this is going to be true for any pair of sets, S and W. I apologize for drag. I have to give a demo, so I have to like do all this stuff. Okay, so here's the proof. This is the proof. Let F be an injection from S to W. Let G be an injection from S to W. And now I'm going to write a recursive definition, the least fixed point recursive definition of the set of the subset of S that where you have to use F, right? And you can write this as a recursive definition. You have to use F if there's no value of G that maps to it. And that means that if you take where F goes, in a place where you have to use F, you can't use G from there. So wherever G goes from there has to use F. So it propagates, right? And that's what this definition of use F says. So we can think about infinity. That means a computer can think about infinity. So it can understand this definition as defining an infinite set. And then we define our bijection. So our bijection is a function that says if we have to use F, use F. If we have to use F, the return value is f of x. If we don't have to use F, find the y, w, such that g of y equals x, and return that y. Is that parsing? Okay. My demo. So I'm restarting this. So there's nothing in here except the foundations of mathematics. I've got like 15 primitives that define the foundations of mathematics. I define an injection. For every output value, there's a unique input value that maps to it, at most one. I define a surjection. I define a bijection. And I read the proof. That's my demo. Now, there's a little bit of development for the demo going on here. When you develop for the demo, you're kind of testing on your training data. So, so I have no right to claim anything. I did try very hard to make the machinery that did this general, but this requires a lot more verification before I.
Okay, but it verified?
It verified it.
Where do we see that? I'm confused.
Oh, that it would have complained if it.
Oh.
Can you break it just so we can see you complain?
Let me try. Let me start over again.
Nice.
Okay, just to show you the contrast, this is the lean proof of the same theorem. And I have a really hard time reading it, but I know it's the same proof because there's the word monotone in here. The recursion is monotone. And there's an LFP right there, which means least fixed point. So it's the same construction, but it's really
Are you using like functional programming and lean is not or something like that, which helps you?
Wait, for the time being, I'm keeping my algorithms proprietary.
Oh, okay.
So, but is it decidable? I mean, is deciding whether with the so actually
No, this didn't prove that the other one was false.
No, but if you is the following problem decidable? Having checking whether Alfred proof is valid. Is that decidable?
No, it's not even really a well-formed question.
Wait,
Let me
I thought
rephrase
that's
it.
what
Let me
you-
rephrase it. Alfred is something that will take a statement and try to prove it. And there's a set at which it succeeds, but if I do one more day of development, that'll be a different set.
So you showed us that if you messed up your proof, it told you this is not a valid proof statement.
No, it didn't say it's not a valid.
Oh, so what did it say exactly?
It said I can't do it. I can't find it.
Ah, okay. So it never said it never says this is wrong. It just says I can't.
The mechanisms as they exist now will not try to refute it. It just tries to prove it.
No, not to refute the statement. To say that the proof is wrong.
There
Maybe
are
I don't
some
understand what an alpha
things.
proof is.
There
right?
are
But
some.
in
There are some things that have that flavor. If I apply a function to an argument, if it can't prove that argument is in the domain of that function, it will complain. It'll stop and say, "Look, you wrote an ill-formed application."
Okay, but that's like a syntax error. It's not a.
Well, it can be an arbitrarily hard theorem actually, because the domain of a function can be some.
Okay. But okay, in Lean, just if I understand correctly, in Lean, if you give the problem of deciding.
No, if you call a lean tactic, and it fails or gives you, there's no characterization of the tactics,
No, that's true. But
and that's what this is.
oh, so you're saying that under.
My system is purely declarative. You never call a tactic. You just say, "Can you prove this?"
Right.
But in Lean, you call tactics. But when you say, "Can you prove this?" the only possible answer is yes or I can't.
I'm not sure if it's the same confusion, but I think I'm a little confused. Like, if Alfred does successfully run, is the statement is completely formalized true at that point, just like in Lean?
Just like in Lean. If there are no bugs.
Just to clarify maybe on the earlier question, so I know that like in Lean and Coq and so on, they make a big point that there is some, well I know there's
Proof
maybe,
term.
well there may be some complication with tactics, but like basically it's decidable. Like if I give you a
Type
.env
checking is
file,
decidable.
right, so in Alfred is it also similar?
No, and I tried to talk to some Lean people. I've got a feature in this language called assert. This assert right there. That's saying the set is going to be defined by a property that the elements have to have. It's sort of like saying the set of, and then you write a formula. And if you put that feature in the type system, type checking becomes undecidable. So this has an undecidable type correctness property.
Is it like very fundamental to the system that it be undecidable?
My belief is that it's fundamental to the performance of the system that you add this feature that makes the type system undecidable. That's
Do people develop machine proofs of the proof checkers themselves? Is there anything-
people do that. So there's, to at least some extent, Coq was verifying itself.
Yeah, it seems convoluted. I mean, I was just kind of thinking about you say if there's not a bug, so if we're really worried about the bug, just have to check carefully ourselves at the end of the day.
You have to worry about Russell's paradox, but it's not actually an issue. You can verify. You could verify itself. You add a little axiom.
Okay.
My understanding is that the existing proof systems intentionally try to make their kernel as small as possible, like some 1,000 lines possibly even, so that if you have enough eyes looking at it,
It increases your confidence. It's going to be harder to know that this is bug-free. But we trust compilers. Compilers are huge. Yeah, let me do one more slide. All right, so there's a whole nother talk that starts here. There are many verifiers. There's Isabel, there's this EQ solver. However, Lean dominates. It's favored among mathematicians. So why? What's Lean's big advantage? And I claim that this is it. I call it the grammatical functor property. Lean's type system, dependent type theory, has this magical property that if you write a well-typed map, say a map from groups or a map from manifolds to their fundamental group, right? A complicated map, or a map from a graph to the spectrum of the graph Laplacian. Really complicated thing. The grammatical checker is going to guarantee that that map is a functor, that it respects the structure of isomorphism. If you have isomorphic inputs, you get isomorphic outputs. And we understand that naturally. When I took topology, they say, what are the invariants of manifolds? Well, we construct these invariants, these properties, these groups, so that we can prove the two manifolds aren't isomorphic. And nobody even bothered to ask, what do you mean if the things are isomorphic, their groups are going to be isomorphic? Because that was obvious. And it's a grammatical, and the claim is that dependent type theory makes this fact, that anything you can define that's grammatically correct has this functor property. And the question is, that my bugaboo is, does that require constructive mathematics? Because the only system we have that has that property right now is this constructive type theory. So I've got a whole talk about how you don't need to do that.
Sorry for one question. Because you talked much about constructive mathematics, do you have any examples of like proofs or features in Alfred that shows how you would be able to construct like non-constructive proofs in a way that you can't, etc.?
Well, there's these classical examples of non-constructive proofs. It's basically what is typically said is that constructivists don't accept the excluded middle.
So I think like in like cognitively they do have like a reductio.
So what they do is they take a constructive type theory and then they add something that gives you the excluded middle and something that gives you the axiom of choice. So it's not really a limitation on what the system can do. It's just a philosophical. I think it really obscures the system when you have to say A implies B means that there's a function from the type. The propositions as types paradigm, I find obtuse. It makes it harder. It's a barrier to entry because it's not natural, and it's just not needed.
I guess do you have any like nice example of something that's hard to express in that paradigm that you think is much easier to express with Alfred?
Well, the lean people put a lot of sugar in there, right? And with all that sugar, the idea is you make it invisible. You make the constructivity sort of invisible. It looks more natural. So it really is more of a philosophical point. I mean, there's this point about these assert types, these putting formulas into the type system. What makes it undecidable is a real issue. Okay, I'm done.